Today we're going to talk about the data link layer, commonly referred to as layer 2. So what we have here is a simple LAN. Consists of essentially two PCs connected to a switch. We'll assume for now the switch is in its default configuration, which means all the PCs are in the same VLAN, VLAN 1. So we have here is we have PC1. We're going to be referring to as PC1. PC2 will be referred to as PC2. We have the two MAC addresses. Instead of putting full, MAC addresses, I should put MAC address of A and MAC address of B. And then we have some IP addresses, x.x.x.1 and x.x.x.2. This indicates they're on the same subnet. The first three octets are the same. I just wanted to use non-numbers to try to make things simpler to understand. So in this case, when PC1 sends traffic to PC2, it will send traffic to the IP address of PC2. So for example, ping we're all familiar with. If from PC1 I ping PC2, I would ping x.x.x.2, and that traffic would get transmitted across this link, and the switch would forward that traffic out to PC2. Now when this traffic is actually transmitted at layer 2, it is transmitted using MAC addresses. And we'll get into that in a little bit more in a few minutes. But first, let's talk about Ethernet frame. As I mentioned, we have the MAC addresses are what we use at layer 2. This is what the frame looks like. This is a destination MAC address. The first field, 6 bytes, 48 bits, is the destination address. The source address comes next. The third field is the type field. The type field indicates what type of data is actually being carried in this frame. That data is carried here, and the next section of the frame carries the data. The type field indicates what kind of data that is. So that's how the Ethernet layer knows which next upper level layer it needs to give the data to. And then the last thing is the CRC, which is basically an error check to check the frame did not have any errors during transmission. So I have this abstract idea of upper layer data dropping down into the frame. So the frame carries whatever data it's given, and that data comes from an upper layer in the protocol stack. Usually we'll see IP or ARP or maybe IGMP or something else like that. Not IGMP, ARP. IGMP is not a good example. So anyway, the minimum total length is 64 bytes. The maximum total length is 518 bytes. So if you look at these numbers, 6 and 6 is 12, and 2 is 14, and 4 is 18. 18 and 46 is 64. So we have the header fields and the minimum size of data. And then the maximum length is 1500 bytes of data plus 12. And 2 is 14, and 4 more is 18. So 1500 plus 18 is 1518. So you may have heard the term maximum transmission unit before, MTU, which is 1500 bytes for Ethernet, and that is what that means. This is where the 1500 bytes come from. That's the maximum amount of data that can be sent in an Ethernet frame, and that was dictated by the protocol design. The 46 here is the minimum amount of data. Why do we have a minimum amount of data? Well, I'll talk about CSMA in a little while, but basically that is the amount of data that will ensure that once a station starts transmitting, that every other station on the link had the opportunity to hear it before it stops transmitting. So this is Ethernet frame. I said before, the type field indicates what type of data is being carried. To demonstrate that a little better, I have another example here. This is the actual type value for an IP datagram, and then here's my sample IP datagram that falls down into the data portion of the Ethernet frame. So some application up here said, hey, I need some data to get sent. It passed it down to TCP or UDP. UDP or TCP passed it down to IP, and now IP has encapsulated it and is going to pass it down to the frame to be sent. As I mentioned a minute ago, we're talking about CSMA. That is the access method for wired Ethernet, carrier sense, multiple access, collision detection. So let's go through that for a minute. Carrier sense means that all stations will be listening on the link. for other people to send. Multiple access means multiple stations have access to the same link, and collision detection means they try to listen for collisions. So what does that mean? How does it work? Well, if you want to send something, you listen for a short period of time to make sure that nobody else is sending at that same time. If someone else is sending, you wait. When it's clear, you try to send. While you are sending, you keep listening. If you hear someone else sending while you're sending, that's called a collision. And at that point, you stop sending, and then you wait some random amount of time, and you try again. You listen to see if anybody's sending. If they're not, you start sending. Continue to listen while you're sending. If you make your entire transmission and you do not hear anyone else sending at that same time, then you can be relatively certain that there was no collision, and you can go on about your business. So this slide says that gets disabled for full duplex. Full duplex means you're sending and receiving at the same time, which is usually what happens when you're connected directly to a switch port. CSMA CD is only really necessary if you're using hub or, God forbid, some sort of coaxial bus where other people might be sending at the same time. If you're on a switch port and you're the only one off that switch port, then usually CSMA CD is disconnected and you're configured in a full duplex, sending and receiving at the same time. We talked about MAC addresses a little bit. Let's review those. 6 bytes long, that'd be 48 bits. The first half, or the first 3 bytes, identify the manufacturer, and then the second half is a unique number, one-up number, to uniquely identify the MAC address. Normally, MAC addresses are associated with the network interface card. They're also oftentimes called burned-in addresses, but they can be changed in software. And then we have this whole idea of virtualization where they're not even really real at all. They're just associated with a software interface. We have 3 types of MAC addresses we might experience: unicast, multicast, and broadcast. A unicast MAC address is a MAC address that's used in a one-to-one communication, so we have one sender sending to one recipient. A multicast MAC address would be a MAC address used in a one-to-many situation where you have one sender that wants to send to one group of recipients. And then a broadcast MAC address would be what gets used if one node wants to send to all nodes on the network. And we'll see that example of that when we talk about ARP. So let's talk about what happens when we go back to that ping packet that I talked about at the beginning from PC1 to PC2. Right, if PC1 was to ping PC2, if we look over here, we have a IP datagram that contains the ping, the source IP address x.x.x.1, the destination IP address x.x.x.2. That gets put down in an Ethernet frame. The Ethernet type gets set to IP, and then the destination address, which was that was our first field in the Ethernet header. The destination address, MAC address, is B, and the source MAC address is A. So if we look, the MAC address is B, the source is A. So this frame leaves this PC, gets to the switch examines the destination MAC address, which is B, and usually knows that it needs to send it out this switch port to PCB. So that's how that works on a local area network. One thing we need to have to make this happen is the MAC address for the remote node. How do we go about getting that MAC address? Do we have some sort of table that lists all possible MAC addresses of all nodes ever created on our PC? Is that how it works? No, we use, oh crap, got ahead of myself. For the reply from PC2 to PC1, it's the opposite. The source IP address is x.x.x.2. The destination IP address is x.x.x.1. This IP datagram gets encapsulated in the Ethernet frame, and this time the source, the destination MAC address is A, and the source MAC address is B. So this is from PC2 to PC1. The destination MAC address is A. So the frame goes into the switch. Switch examines the Ethernet header and says, oh, this frame's for MAC address A, that's on this port here. So how do we know which MAC addresses go with which PCs? We have some magical table that lists every MAC address ever created? No, we don't. We use the Address Resolution Protocol, or ARP, So essentially, when we want to know the IP address of a particular host, we send an ARP request, right? If we look at the very top thing on the screen, well, not the very top thing, the very top thing says ARP. The second thing down on the top of the screen, we see an ARP request and an ARP reply. If you'll note, the ARP request is sent to the broadcast address. Why is it sent to the broadcast address? Well, I'm trying to find the MAC address for the host. We send at layer 2 MAC addresses. So if I don't have the MAC address of the host, how could I send it a frame to find out its MAC address? So basically, I send a request to the broadcast address because I know all nodes on the network will receive that frame. And essentially, I'm looking for a particular IP address. So in this case, I'm looking for the IP address of 172.16.99.254. And then I'm telling them who I am. I'm 172.16.99.211. So essentially, whoever has this IP should hear this broadcast request and then respond with their MAC address. And that's what happens. The second frame we see here is a reply from the host at 172.16.99.254 informing me what their MAC address is. So if we look at the details in the frame, we see I highlighted a couple things that are interesting to me. First thing is in the ARP request, the destination address is the broadcast address, which I just said. And then the other thing that I found to be more interesting was the target MAC address in the ARP portion of the packet was all zeros. So since the sender does not know the IP address, does not know the MAC address, this field gets set to all zeros. That's the information they're looking for. All right. Here's the ARP reply. In this case, the destination is the station that sent the request. We look up here, the request was from 5894-6B750228. Now we're sending it back to 5894-6B750228. Down here, all these fields are filled out this time. So that was an ARP request and an ARP reply. Again, ARP is used to find out MAC addresses for IP addresses that you want to send traffic to, but you don't currently have the MAC address. So here's the same ping we were talking about, but this time we're going to look at the ARP traffic that's necessary to make it happen. So here we have an ARP from PC1 to PC2. A ping from PC1 to PC2. The first thing that happens is PC1 sends a ARP request out that says, hey, I'm looking for x.x.x.2. I've indicated that up here in my upper layer protocol section. The zero here represents the all zeros we saw in the ARP request field. It's sent to the broadcast MAC address. The source MAC address is set to A, and we have the type field is set to 0x0806 in this case, which is ARP. The next thing is an ARP reply from PC2 to PC1. So this is our ARP portion of our packet we're representing with the B is a MAC address for PC2, the IP address of PC2, and then the MAC address of PC1 and the IP address of PC1. This becomes our payload for our Ethernet frame. Again, the type field 0x0806, which represents ARP. And then we have the unicast reply. So the ARP request is broadcast. A ARP reply is unicast. So after we get the MAC address, then we can go ahead and send the ping. This is the same ping we looked at a minute ago. Destination, MAC address B, source MAC address A, types IP, and here's our ping. And then we have the reply from PC2 to PCA, same thing we saw a minute ago. So that's how the request works with including the consideration of the ARP request in the packet. So what happens if we need more than one subnet? So in this case, we have our original two PCs in the x.x.x subnet, and I've added two more PCs in the y.y.y subnet. In this case, if they're all plugged into the same switch, everything will work as expected, but there's no segmentation. They're all in the same collision domain. Frames from PC3 can reach PC2 because they're all connected logically to the same a local area network. So if you have separate subnets, you probably want them to be separate at layer 2. So the way you could do that is you could have more than one switch, or you could use VLANs. With VLANs, we configure the switch in a way that says, hey, the port that PC1 is connected to and the port that PC2 is connected to are considered in VLAN X, right? And the port that PC3 is connected to and the port that PLAN 4 is connected to, PLAN, did I say PLAN? PC4 is connected to is in VLAN Y. So we configure our switch in that way, and now these PCs are logically separated from these PCs. Their frames cannot reach each other's interfaces because the switch won't let that happen. So now, in this case, PC1 can talk to PC2, PC3 can talk to PC4, but they cannot connect to each other directly at layer 2. And at this point, they can't connect to each other directly at layer 3 either because they are in separate VLANs, and there's something else we need for that to happen. So that's how we can logically separate those two subnets. So if PCs are in the same VLAN, they need to be on the same subnet, right? So here we have PC1 and x.x.x.1 and PC2 is x.x.x.2. They're the same subnet. We wouldn't want another PC up here, PC9, that's y.y.y.3. That would not work because they need to be in the same subnet to communicate. The same subnet is a layer 3 concept related to IP addresses. Down here we have VLAN Y, y.y.y.1, and y.y.y.2. So to summarize, PCs in the same VLAN need to be on the same subnet. PCs in different VLANs need to be in different subnets. So how we go about configuring this? Basically, for each interface we are connected to, we would go into our Cisco switch. These configuration commands I'll be giving you guys are for Cisco switches. You'd obviously get into the configuration, enter enable config T, which I left off. You guys should know that by now. And then the particular interface you want to configure. In this case, I marked it as Z. But if PC1 was connected to interface fast Ethernet 01, you would put interface fast Ethernet 01, and then switch port access VLAN X. That's the easiest way to do it. X would be an actual number, so this would be like VLAN 7 or something. That would make it happen. Another option, oh, I left the other option out. So when you do this, if VLAN Z does not exist, it will get created for you automatically. If you wanted to create the VLANs in advance, you could certainly do that. Say we have more hosts, or our hosts are not physically close enough that they can be connected to the same switch. How do we make that happen? In this picture, we have two PCs that need to be in the same subnet, in the same VLAN, connected to two different switches. At this point, the switches aren't connected together, so at this point, there's no way these PCs could communicate with each other. So what we need to do is we need to connect those switches together, and the way we normally do that is with a trunk link. What is trunking, you may ask? Well, trunking is when you send traffic for multiple VLANs across a single link. That traffic going across the VLAN, across the link, gets tagged with the VLAN header, so the receiving switch knows what VLAN it needs to go into. First, let's talk about how you configure trunking. Whichever switch port the other switch is connected to, so say this was FA024, you would go in and configure it in int FA024 switch port mode trunk, and that would configure it for trunking. A command you could use to verify that, which I didn't include, would be show interface trunk. Would show up and hopefully show you which interfaces were trunking. If you expect trunking to be happening and you enter the command show interface trunk and nothing shows up, then something is not right. So anyway, let's go back and talk about trunking. Is defined the most common, the predominant method of trunking you run into nowadays is 802.1q. Before Cisco had a Cisco proprietary inter-switch link, or ISIL, that you might see referenced somewhere, but it's not nearly as common anymore as 802.1q. Way it actually works is we take our Ethernet frame, which you should recognize from earlier in the slides. Take your Ethernet frame and you stick a tag in the middle of it to indicate what VLAN that traffic belongs in. So if we look at our example of a ping from PC1 to PC2 across the trunk link, right, we have our IP datagram that says, hey, this is a ping from x.x.x.1 to x.x.x.2, right? We get that put into a frame, and that frame gets sent from the PC to the switch. This is what the frame looks like from the PC to the switch. It has a type header, type field indicating IP, destination MAC address of B, source MAC address of A. That's what it looks like between the PC and the switch. Next thing we have is we have it between the switches. If you look between the switches, it's identical to before, except now we have the VLAN tag indicating what VLAN this traffic belongs to. So then once it gets to the other switch knows how to process it. And once it does that, it's going to send it out to PC2, and it will remove the tag. So the traffic that gets sent to VLAN 2 is not tagged. So, so far we've been talking about communicating between two PCs on the same VLAN. Well, what happens, or what do we need to do if we want to communicate across VLANs? Well, as soon as we want to go across VLANs, we need to have a device that can perform routing. There's two primary options for that. One would be a layer 3 switch, and one would be a router. In this case, I put a little router icon on top of my switch to indicate that it's a layer 3 switch. So on that layer 3 switch, we would create VLAN interfaces and associate IP addresses with that, and then we would use that IP address as the gateway. As you'll see now, I've added a gateway to my PCs. The gateway is what your PC uses when it needs to send traffic to a different network. So just communicating between PC1 and PC2, I did not need a gateway because they were on the same local area network. But now that I'm going to try to communicate across VLANs, then I need to have a gateway. So let's talk about what's going to happen on a ping from so let's talk about what's going to happen from ping from PC2 to PC4. We're going to look at a couple different concepts that we want to be familiar with in this case. One, when we are sending traffic at layer 3 or the IP layer, we are sending from the source IP address of the original host to the destination IP address of the host we desire to get to. So if we look at my IP datagram, this IP datagram is from x.x.x.2, and the destination IP is y.y.y.2. So I'm trying to send from this PC's IP address to this PC's IP address. But to make this happen, it has to go to my gateway. So the first actual hop that I send this packet is to the MAC address of my VLAN interface. See, the MAC address of my VLAN X interface is E. So I'm going to send this traffic to my VLAN interface on my layer 3 switch for routing, right? So on this link, this is what the frame looks like. The next thing that needs to happen is my frame needs to go across my trunk link. What's that going to look like? That's right. I'm glad you're paying attention. You're right. It is going to have a VLAN tag in it for VLAN X. It's very, very good paying attention of you. So across this link, it's going to still be from to MAC address E from MAC address B, right? I'm sending it to my gateway, which is this VLAN interface. It's get tagged for VLAN X. When it gets to the layer 3 switch, the layer 3 switch is going to process it. It's going to remove the Ethernet information. It's going to look at the destination IP address, which we'll talk more about routing in a few weeks. It's going to check its routing table, see, oh, y.y.y.2, that's directly connected to me. I need to send that out in VLAN Y. So it's going to re-encapsulate that. It's going to stick it, sorry, it's going to re-encapsulate that, and when it's going to send it across this trunk link, it's going to stick a VLAN tag on there for VLAN Y, because we're now operating a VLAN Y. And if we look at our destination MAC address, it's now, I screwed that up. Yeah, I screwed that up. The destination MAC address should be D, and the source MAC address should be F. God, I'm going to fix it. D, D, F. So now we see that when it gets sent from the layer 3 switch, the MAC address is now destination of D and source of F. So it's going from this VLAN Y interface to the PC4 interface, right? And it is going across a trunk link, so it's tagged for VLAN Y. And then the final step across is across this link from the switch to the PC. And the source MAC address is still F because it's still from the VLAN Y interface, and the destination MAC address is D. So let's take a moment to think about what would the reply from PC4 to PC2 look like. Well, we're going to go from PC4 to PC2, so this first hop. Well, actually, let's talk about the IP. The IP header is going to stay the same all the way. This will be y.y.y.2 to x.x.x.1 in the destination, y.y.y.2, x.x.x.1, y.y.y.2, x.x.x.1, y.y.y.2, x.x.x.1. So that'll be that. Let's look at our Ethernet frame. It's going to be from PC4. So PC4 will be the source, and the first hop we will send to the VLAN Y interface because that is the gateway for VLAN Y, and PC4 has to send the traffic to its gateway to get the traffic off the network. So it will be to MAC address F from MAC address D, right? Across this link between the switches, it's still going to be to F from D. It's going to be tagged for VLAN Y, right? It's going to get processed by the layer 3 switch. The routing nonsense is going to happen. Now it's going to be to MAC address B from MAC address E, and the field here for the VLAN tag is going to be VLAN X, and then the final delivery from the switch to the final PC is going to be from MAC address E to MAC address B. So just to recap, hopefully understand, layer 2 deliveries are by MAC addresses, layer 3 deliveries are by IP addresses, and for one single layer 3 delivery there can be more than one layer 2 delivery, and if you're going to something off of your network, there will be more than one layer 2 delivery. PC4 reply to MAC address F from MAC address D, tag it for the VLAN, and then to B from E, tagged for the VLAN, and then finally delivered. So here's some commands to configure your switch interfaces. Right, we need trunking between the two switches, which should have already been configured, and then to create VLAN interfaces on the Cisco switch, assuming you're already in the config mode. Interface VLAN X. Interface VLAN X will create the VLAN interface, and then you assign the IP address and the subnet mask. Interface VLAN Y creates the other interface, and you assign IP address, subnet mask. And I can't recall if you need to do a no shutdown on a layer 3 switch interface, on an VLAN interface or not. You may need no shutdown. If it doesn't work, then try no shutdown. So another option for that same thing we just did with the layer 3 switch, we could also have a router connected to the switch. Sometimes this is called inter-VLAN routing, sometimes referred to as router on a stick, the way the router is just stuck off the switch with a single link. And it works exactly the same way that we just saw with the layer 3 switch, but instead of it just going to the switch and back down, now we have an extra hop to the router. And to configure the router for that, well, configure the switch for that, you need the switch port that the router is connected to. It needs to be configured for trunking. And the router interface, assuming this is FA00, first you do a no shutdown on the physical interface, then you enter interface FA0/0.x to create the sub interface. predominantly people use the same number for this X that they're using for the VLAN, but it doesn't have to be the same. Encapsulation, I spelled that wrong. That's awesome. Encapsulation. I guess that's what that squiggly line means, right? It's spelled wrong. Encapsulation. All right, so encapsulation.1qx, then the IP address for that subinterface, fa0/0.y, create another subinterface for the other VLAN, encapsulation.1qy, and the IP address on that subnet. As far as the delivery of the traffic, it's going to be the same way. First hop will be, assuming PC4 to PC2, the first hop will be to MAC address F from MAC address D. It'll be tagged. It'll get processed. The tags will be removed. Tag will be added. And then down here it'll be from MAC address E to MAC address B. So we talk primarily about Ethernet, which is the main layer 2 protocol we're going to be worried about in this class and our studies of local area networks. There are some other layer 2 protocols. 802.11 Wi-Fi has its own set of layer 2 protocols and its own access method. If you're interested in that, we have a wireless class you can take. PPP, point-to-point protocol, PPP-TP, point-to-point tunneling protocol, HDLC. Those are some WAN protocols we might run into on our serial links as we start connecting to other routers and doing some other fun stuff. So, summarize, Ethernet is the primary layer 2 protocol we're going to run into on wired LANs. There are different speeds. 10 meg, 100 meg, a gig, 10 gig, but they all have similar or the same format and all kind of work similarly. MAC addresses are used to deliver packets at layer 2 and used as the addressing in the layer 2 header. IP addresses are used at layer 3. MAC addresses change hop by hop as the layer 3 packet is being delivered. IP addresses stay the same end to end most of the time. There are things like NAT to consider. We'll talk about that later. ARP is used to get MAC addresses, so when we start out trying to connect to something, we don't actually enter the MAC address. We usually give it an IP address or a name that gets translated to an IP address, but at some point our machine actually has to send that frame using a MAC address. Devices in the same VLAN need to be on the same subnet. Everything that was x.x.x.1 or x.x.x.2 need to be in the same VLAN and on the same subnet. Trunking allows frames from multiple VLANs across the same link by inserting a VLAN tag. That's where we put the 802.1q tag in the middle of the Ethernet frame so the switches know what VLAN it needed to be associated with. Routing is needed to send traffic between VLANs. So if we have machines in different VLANs, they need to be a router somewhere to get traffic between them. So do you have any questions? If so, post it to the discussion board or bring it to class. You could, I guess, potentially send me an email, but then other people who don't have the same, who might have the same question as you would not benefit from your question. So it'd really be preferable if you could put it on the discussion board or bring it to class.